Hi friends, I am Mohan. Welcome to the channel Kerala Neet Academy and the Neet Mission 15 days. In my last video, I explained some simple numerical examples relating to three topics, namely units and measurements, one-dimensional motion and two-dimensional motion. Today, we are going to cover some simple and important numerical applications from the two topics, namely Newton's laws of motion and work energy power. Especially as far as the part of mechanics of physics is concerned, there is a wide scope of having misconceptions. Generally, most of the students unknowingly they may be developing some misconceptions. If you go to the competitive examinations with the misconceptions in your minds, no doubt you will commit mistakes in solving numericals. Today, the title of our session is Enlightenment of Misconceptions and Applying Conceptual Methods in Solving Numericals. Okay, let us move. Let us start. Look at the first question. A man is sitting in traveling train and facing the engine. He tosses up a coin and the coin falls behind him. It can be concluded that the train is. See, if you look at the motion of the man and the stone from the ground frame of reference, as soon as that man is releasing the stone, that stone will move under gravity. And man moves with the same velocity as that of the train. If you look at the case of that stone, as soon as he released, that stone gets the same velocity as that of the train by means of inertia. That means the horizontal velocity component of the stone is the same as that of the train at that moment. So if you look at the motion of the stone from the ground, it moves along a parabolic path. It will have two components, one in vertical direction, other in horizontal direction. In the resultant motion, it will go in a parabolic path. See here, for that man to catch that stone after some time, the horizontal distance traveled by the stone with respect to the ground should be same as the horizontal distance traveled by the man. Suppose at the moment that stone is released, u be the velocity of the train in horizontal direction. At that moment, the velocity of the stone also will be u in the horizontal direction. If a train accelerates in the forward direction, then the speed of the man increases in the horizontal direction. Therefore, in the given time, the distance traveled by the man will be more than that of the distance traveled by the stone, so that he cannot catch that stone. It will fall behind the man. So in order to catch that stone, with how much velocity that stone is moving in the horizontal direction, man also should move with the same velocity in the horizontal direction. So for this particular question, answer will become moving forward and gaining speed. Come to the next question. A 0.5 kg ball moving with a speed of 12 meters per second strikes a hard wall at an angle of 30 degrees with the wall. It is reflected with the same speed and at the same angle. If the ball is in contact with the wall for 0.25 seconds, the average force acting on the wall, they are asking us to find out. See, you are very much familiar with the concept of average force. By the definition of average force, we are having the formula average force acting over the body will be given by average force is equal to change in momentum divided by time interval. This is the basic equation we are having for calculation of average force. In the last video, we have discussed the differences between average value and instantaneous values. Instantaneous force will be given by the equation rate of change in momentum of the body. Be careful regarding these two factors. Okay, in this particular question, they're asking us to calculate average force acting over the wall. They're asking us to find out. Okay, see, if you look at this diagram carefully, this is the direction of initial direction of momentum of the body. Here, the mass of the particle is given 0.5 kg and the speed of the particle is given 12 meters per second. Therefore, the magnitude of momentum of the particle will be given by 0.5 into 12, nothing but 6 kilogram meter per second. 6 kilogram meter per second is the magnitude of momentum. Initially, that particle is moving in a direction by making an angle of 30 degrees with the wall like this, by making an angle of 30 degrees. So this is the direction of initial momentum of the particle in this example. If you resolve this initial momentum into two components, one component which comes along positive x-axis will be given by the magnitude of this momentum is 6 kilogram meter per second. Already we have calculated. So the horizontal component will be 6 sine 30 degrees. Nothing but 3 kilogram meter per second is the horizontal component. And the vertical component will be 6 cos 30 degrees we are getting. So this will be equal to 6 into root 3 by 2, nothing but 3 root 3 kilogram meter per second. Now, initial momentum of the particle is having two components. One component along the x-axis and another component is along the y-axis. By using unit vectors, we can express initial momentum of this particle as 3 I cap plus 3 root 3 j cap. This initial momentum of the particle before collision. After collision, if you look at the diagram carefully, that particle is moving in this direction after collision. After collision also it is given, it is moving with the same speed, which means it moves with the same magnitude of momentum. So the magnitude of momentum of this particle after collision also will be 6. So if you resolve this final momentum into two components, one component of this momentum will come along y-axis, just like in the previous case. It is nothing but 6 cos 30, nothing but 3 root 3. And other component will come along negative x-axis. Negative x-axis component will be 6 sine 30 degrees, nothing but 3 kilogram meter per second. So one component of final momentum is along negative x-axis, other component is along positive y-axis. If you observe this example carefully, along y-axis there is no change in momentum of the particle. So that particle is undergoing the change in momentum only in horizontal direction. Anyhow, let us find out all these factors. So let me express this final momentum of the particle in unit vectors. So final momentum will be equal to one component is along x-axis, which is nothing but 3 minus I cap plus one component along y-axis, which is nothing but 3 root 3 j cap. In this particular example, in a time interval of, it is given very clearly, in a time interval of 0.25 seconds, they're asking us to find out the average force exerted by that particle over the wall. They're asking us to find out. Therefore, the average force, by the definition already we are having, this final change in momentum divided by time interval. So final momentum minus initial momentum. If you subtract this momenta, then we will get it as 6 minus I cap we are getting by subtracting it. The components along y direction will be cancelled. Divided by time interval they have given as 0.05 seconds they have given. So time interval here it is given 0.25 they have given. So by solving this particular equation for average force, you will get average force will come out to be average force total, it will come out to be 24 newtons minus I cap we are getting. 24 newtons minus I cap we are getting. Which means during this collision of the particle with the wall, that wall will exert the force over the particle along negative x-axis. And the magnitude of that average force will be equal to 24 Newton. So in the same way, we can say that the particle will exert force over the wall along positive x-axis. That value also will be equal to 24 Newton. Action and reaction forces. This is the question based on the average force. Let us see the next question. Look at this question. This particular question is based on the concept of what we call impulse. Here it is given a graphical representation between force and time interval. We know that the area under force time graph represents change in momentum of the particle or impulse imparted to the particle. In this particular example, they're asking us to find out the amount of impulse which is imparted to the particle. They're asking us to find out. Here the shape of the graph is given semicircle. Therefore, the area under this graph in this example, area under this graph represents general equation for area of this semicircle will be pi r square by 2. So from this graph we can write pi by 2 into, here care must be taken. Along y-axis we are having the physical quantity force. Along x-axis we are having the factor time. Already we have practiced impulse in terms of the product of force and time. Therefore, in place of r square, especially relating to this type of numericals, you must express it as the products of r1 and r2. r1 is the radius along y-axis and r2 is the radius along x-axis. Therefore, from this equation we can write pi by 2 into f naught into t2. If you look at this graph, the radius along that x-axis, which is nothing but t naught by 2. Therefore, this will be t naught by 2. Therefore, this will be pi f naught into t naught by 4. So, impulse imparted to the particle in this particular example will be given by this particular equation. Pi f naught into t naught divided by 4 we are getting. Okay, look at this example. Two blocks A and B of masses 2m and m respectively are connected by a massless and inextensible string. The whole system is suspended by a massless spring as shown in the figure. The magnitudes of accelerations of A and B immediately after the string is cut are respectively. Okay. Before that string is cut, let us calculate how much amount of spring force is existing in the spring. Look at this diagram, all of you. If you take these two blocks together as the system, here, the tensional forces between the blocks will become internal forces. They will be cancelled. Tensional forces will be cancelled. Okay. Now, total mass of the system here, it is nothing but 3m. Total mass of the system is 3m. On this block, totally two forces are acting. One is the weight of the block 3mg. Second one will be the spring force. As the block is in equilibrium, the spring force will be equal to 3mg. Okay. Now let us see what actually they are asking us to find out in this particular example. As soon as that string is cut, they are asking us to find out the magnitudes of accelerations of the block A and B. Okay. As soon as that string is cut, the tension in the string will become 0. Once the tension becomes 0, that block B falls under gravity. Therefore, the acceleration of this block B is nothing but acceleration due to gravity. So block B falls under gravity with an acceleration of magnitude equals to g. And if you come to the case of that block A, now that block A is acted by two forces. One force is weight of that block, nothing but 2 mg, and other part is spring force. Okay, here one very important point which must be practiced is immediately after that string is cut, that spring does not undergo any kind of new deformation. What I mean here is, as soon as that string is cut, there won't be any change in the value of the spring force. So for the spring force value to be changed, additionally that deformation has to take place in the spring. But here immediately that deformation does not take place. Therefore, that spring force remains as it is. This is the very important point which must be practiced. Therefore, spring force already we have calculated. That value of spring force is nothing but 3 mg. If you look at the free body diagram of this block A, one force is weight of the block acting downwards. Other force is 3 mg acting in the upward direction. Therefore, that block A will be accelerated in the upward direction. And the force equation of this block A will be net force is equal to ma according to Newton's second law. Net force is nothing but 3 mg minus 2 mg will be equal to total mass of that block A is nothing but 2m into acceleration of that block A. So from this acceleration of the block A, we can find out it is coming out to be g by 2 we are getting. So as soon as that string is cut, block B is moving under gravity with a magnitude of acceleration equals to g, and block A is moving in the upward direction with an acceleration of magnitude equals to g by 2. Come to the next question. In this question, it is given an arrangements, fully arrangements they have given in the question are identical. The mass of the rope being negligible. In case 1, the mass m is lifted by attaching a mass 2m to the other end of the rope. In case 2, the mass m is lifted by pulling the other end of the rope with constant downward force 2 mg. The acceleration of mass m in case 1 is, okay. It is also a very important numerical. Here, majority of the students, they are having one misconception. Okay, let me clear out that misconception. If you look at this second diagram, in that second diagram, we are applying some force F over the string directly. That force is given as 2 mg. So, dear children, you please remember, in case of a string, any kind of force that we apply over the string, it always represents tensional force. Other than tension, we cannot exert any kind of force over the string. So in particular example, we are pulling the string with the force 2 mg. It means 2 mg amount of tension we are exerting over the string. So the main difference which comes between these two examples is that tensional force. In the first case, over this block M, look at this diagram. Over this block M, 2 mg amount of tension will not act. It will act, how much it will act, that you can calculate very easily. First of all, let us find out the acceleration in case 2. If you come to the free body diagram of that block M in case 2, that block M will be acted by two forces. One force is mg, other force is tension. That tension is nothing but 2 mg. Therefore, this block will accelerate in the upward direction. In the second case, we are talking about the second case. So in this case, the resultant force acting over that block will be in the upward direction. The resultant force is nothing but 2 mg minus mg. So net force is equal to mg. That mg will provide acceleration to that block. Acceleration of this block, we named it as A2. Therefore, acceleration of the block in the second case is nothing but g meter per second square in the upward direction. Okay, it is very clear. Come to the first case. It is a simple pulley system. Without the knowledge of tension, directly by using one equation, you can calculate the acceleration of these blocks. Already in our portions, we have practiced. Acceleration of these blocks will be given by unbalanced force divided by total mass to be pulled. Unbalanced force divided by total mass to be pulled. In this case, the total unbalanced force means weight of 2 mg block minus weight of mg block. So this will be 2 mg minus mg divided by, in this particular example, the total amount of mass which is to be pulled is nothing but 3m. It is different from the previous case. Therefore, this will be mg by 3m we are getting. Nothing but g by 3 upwards. So that the difference of acceleration in both the cases is coming into play because of variation of tension. In the first case, you can calculate the tension by taking the free body diagram of any one of these two blocks. Take this lighter block. Over this lighter block, two forces are acting. If you take lighter block as the system, one is mg and other one will be tension. Already we calculated the acceleration of that block. The acceleration of that block has come out to be g by 3. Therefore, from this equation you can write T minus mg will be equal to mg by 3. So T will be equal to 4 mg by 3 we are getting, which is nothing but 1.33 mg. So while dealing with this type of numericals, you should be very careful. Please try to understand that any kind of force that we apply over the string, it represents the tensional force. So that the tension makes the difference in these two examples. So it's very clear from this, the acceleration in first case is less than that in the second case. Third option will be the answer for the particular example. Okay, come to the next question. In the arrangement shown, the pulleys are fixed and ideal. The strings are light. It is given that M1 is greater than M2 and S is a spring balance which is itself massless. The reading of S they are asking. In units of mass they are asking. Okay. So relating to this type of examples also, students sometimes they are developing misconceptions. Before we solve this numerical, one more simple example let me specify here. All of you look at this diagram. I am taking an example of this pulley arrangements only. Here it is spring balance. Suppose from the two sides, the same amount of mass is suspended. Just look at this diagram. One side mass M, other side also M mass is suspended. Regarding this type of examples, one common mistake majority of the students they are committing. They will give two types of wrong answers relating to this type of example. They may say the reading of this spring balance is either 0, or sometimes they may say the reading of the spring balance as 2 mg. Both answers are wrong. Okay, so one very important point which must be remembered and practiced thoroughly here is the reading of the spring balance here represents the tension in the string. Here the total system is in equilibrium, it is not accelerating. So if you take the free body diagram of any of these two blocks in this particular example, one force is mg and other force will be tension. As this block is not accelerating, the tension in the string will be equal to mg. That means in this particular example, the reading of the spring balance will be equal to mg only. It is not equal to 0 and it is not equal to 2 mg. Be careful. Now come back to the numerical, what we have been discussing. In this particular example, these masses are not equal. Whether masses may be equal or may not be equal, the reading of the spring balance represents the amount of tension in the string. Okay, just look at this particular example. In the previous numericals also, like a simple pulley system or relating to this numerical, the tension in the string will be given by the direct equation. Already you have studied these simple pulley systems. Your tension in the string will be given by T will be equal to 2m1 m2 by m1 plus m2 into G is the equation already we are having. Otherwise, by taking the free body diagrams of these two blocks, you can find out this tension in the diagram. This is the amount of tension which is developed in the string here. So, throughout the system, the same amount of tension will exist because spring is massless and these both strings are also massless. You are very much familiar, if a string is massless, throughout that string, the same amount of tension will exist. So, in this particular example, this total tension in the string will be given by 2m1 m2 by m1 plus m2 into G itself represents the reading of the spring balance. But in this particular question, they are asking us to express that what we call reading in unit of mass they are asking. In this sense, they are asking us to express in kilogram weights. Therefore, the reading of spring balance in this particular example will be given by 2m1 m2 by m1 plus m2, because 1 kilogram weight will be equal to G newtons. This G newtons you can replace with the kilogram weights. Therefore, tension will become 2m1 m2 by m1 plus m2. That is the reading of the spring balance. Okay, come to the next question. A block of mass m is pulled along a horizontal frictionless surface by a rope of mass small m. If a force of magnitude P is applied at the free end of the rope, the force exerted by the rope on the block, they are asking us to find out. Okay, it is also one of the simple examples. Just look at this particular diagram. Here it is given a block of mass capital M they have given. To this block of mass capital M, a rope of mass small m is attached. And we are pulling the other end of the rope with some force of magnitude P. So in this question, we have to calculate the force exerted by this rope, over the block. They are asking us to find out. Initially, let us consider that block and rope together as a system. Let us consider this block and rope together as the system. If you take that block and rope together as the system, then the net force acting over the system is nothing but P. So net force will be equal to total mass of the system into acceleration, m plus m into a. Therefore, in this particular example, the acceleration of the system of that block and rope will be given by a will be equal to, a is equal to P by m plus m we are getting. Okay, this is the acceleration. In this case, we have to find out the force exerted by that rope over the block. This force we have to find out, F value. So this force F will pull that block with the same amount of acceleration P by m plus m. So if you take the force equation for this particular block, that force equation will be given by F is equal to m into a. This is a force equation for that particular block. M into the acceleration is nothing but P by m plus m. Okay. See, if that particular rope is massless, then throughout that rope same amount of tension will exist. This is another important point which must be practiced. That means if rope is massless, mass of the rope is equal to 0. That means small m will be equal to 0. Then the force exerted by that rope over the mass will be equal to P only. In case of massless rope, throughout the rope, same amount of tension will exist. So how much amount of tension we are exerting at one end of the rope, nothing but P, the same amount of tension will exist throughout the rope if rope is massless. But in this particular example, rope is having some mass. That means at the two ends of the rope, that tension is not same. At one end of the rope, the tension is nothing but P. Already we have seen. Whatever the type of force that we are applying over the rope, it represents the tension. So at one end of the rope, we applied the tension, which is nothing but P. As the rope is having mass, it will exert a different tension over the block. That means F in this example. Okay, look at the next question. The masses of 10 kg and 20 kg respectively are connected by a massless spring as shown in the figure. A force of 200 Newton acts on the 20 kg mass. See, look at this diagram, all of you. Over 20 kg block, 200 Newton force they have applied. Okay. At the instant shown, the 10 kg mass has an acceleration of 12 meter per second square. Okay. Let us assume the acceleration of this 10 kg block as A1. That A1 is given 12 meter per second square. What is the acceleration of 20 kg mass at that instant? The acceleration of 20 kg mass is, say, for example, A2. That we have to find out. Okay. Let me convey one important point relating to this particular example. Suppose in this particular example, if that 10 kg block and 20 kg block, if they are connected by means of a massless string and inextensible string. In case of inextensible string, one important property you might have practiced. If a string is inextensible, any number of blocks may be connected to that particular string, they will have the same amount of acceleration. So in this particular example, if these two blocks are connected by means of inextensible string, the acceleration of these two blocks value will be same. But in this particular example, these two blocks are connected by means of a spring. Spring is a stretchable one, which means those two blocks, they do not maintain the same amount of acceleration. If you consider these two particles or blocks together as the system, then the total external force acting over the system is nothing but the 200 Newton. And the spring forces between the blocks will become internal forces. Okay. So for this particular system of two particles of masses, what we call 10 kg and 20 kg, the total external force applied over the system will be given by total applied force will be equal to M1A1 plus M2A2. The total applied force will be equal to 200, that will be equal to M1 is given 10 and acceleration of that first particle is given 12 plus mass of the second particle is 20 and we have to find out that acceleration A2. So from this diagram, it's very clear 20A2 will be equal to 80. Therefore, A2 will be equal to 4 meter per second square. So this is a method of solving the question when two blocks are connected by means of a spring. So 4 meter per second square is the answer to this particular example. Okay, look at this example. This is an example. See, a block of mass M is placed on a smooth inclined wedge of inclination as shown in the figure. The wedge is given an acceleration A towards the right. Find the value of A. Here one simple condition is missing in the question. They are supposed to specify that with respect to the wedge, that block remains in equilibrium, then what will be the acceleration of that wedge? That we have to find out. Okay, that condition is missing in the question. Now, we can solve this question either from the ground frame of reference or wedge frame of reference. See, with respect to ground, if any object which is moving with an acceleration will be treated as an example of non-inertial frame of reference. One important point you remember that when we look at an object from inertial frame of reference, only real forces should be taken into consideration. Whereas when we look at an object from non-inertial frame of reference, along with the real forces, pseudo forces also will come into play. Here, with respect to the ground, that wedge is accelerating. Therefore, wedge comes under non-inertial frame of reference. I solve this particular example from the wedge frame of reference. Look at this diagram. Here, wedge is accelerating along positive x-axis. This angle of inclination they have given as theta. If you look at that block from the wedge frame of reference, totally that block will be acted by three forces. One force is mg, vertically downwards. Second force is normal force from the wedge. And third force will be the pseudo force. Pseudo force will be given by the equation ma, mass of the block into magnitude of acceleration of that non-inertial frame of reference. Here that non-inertial frame of reference is nothing but wedge frame of reference. Wedge is accelerating along positive x-axis. Therefore, pseudo force acts over the block will be along negative x-axis. Pseudo force acts over a body is always in a direction opposite to acceleration of frame of reference. So totally in this example, three forces are acting over the block. And one condition which is given in the question is, with respect to the wedge, that block remains in equilibrium. Equilibrium, I think you are very much familiar. Equilibrium means, especially in this example, it is a translational equilibrium. The net force acting over the block with respect to the wedge should be equal to 0. Now let us balance all the forces which are acting over the block with respect to the wedge here. We can resolve this normal force into two components. This angle also will become theta. So this will be n cos theta. This component will be n sin theta. Now we can balance these forces. We can write n sin theta will be equal to ma. This is one equation. And another equation in vertical direction, n cos theta will be equal to mg. By dividing these two equations 1 by 2, we will get tan theta will be equal to a by g we are getting. So a is equal to g tan theta is the equation we are getting. We can solve the same question from ground frame of reference also, that you can try. Come to the next question. A body is fired with a velocity 200 meters per second at an angle of 60 degrees with the horizontal. At the highest point of its flight, it explodes into three equal fragments, one falling vertically downwards with a velocity of 100 meters per second, the second going vertically upwards with a velocity of 100 meters per second again. The third fragment will be moving with the velocity. So this question is based on the concept of law of conservation of momentum. Relating to conservation of momentum, sometimes students, they are ignoring the idea of conserving the direction of momentum of the system. Okay, now look at this example. Here, that particle is projected with a speed 200 meters per second at an angle of 60 degrees with the horizontal. So that particle moves along a parabolic path. When the particle is at the highest point, the net velocity of the particle is nothing but horizontal component of velocity. Therefore, the net momentum of the particle at the highest point is nothing but mu cos theta, which is nothing but m into u is given 200 meters per second and angle of projection is given 60 degrees. So 200 into cos 60, 1 by 2, nothing but this will be equal to m into 100. So before explosion, at the highest point, the total momentum of the system of that bomb is m into 100 units along positive x-axis. That bomb may be exploding into any number of fragments. The total momentum of all the fragments should come out to be along positive x-axis only in order to conserve the momentum. In this particular example, that momentum will be conserved just before explosion and just after explosion only. So in this particular example, immediately after explosion, it is given, it is exploding into 3 fragments. Out of those 3 fragments, 2 fragments, they are moving in opposite directions, one vertically downwards and other vertically upwards, having equal masses. The bomb is exploding into 3 equal fragments. So now the mass of each fragment will be equal to m by 3. One fragment is moving downwards with a speed 100 meter per second. So the momentum of first fragment will be equal to m into 100 by 3 kilogram meter per second. Second fragment is moving upwards with the same amount of momentum, which is nothing but m by 3 into 100. See here, one important point you just observe. Before explosion, there is no momentum to that bomb system in the vertical direction. Then it may be exploding into any number of fragments. After explosion also, that system should not gather momentum in the vertical direction. So that the condition very clearly they have given in the question here. See, if you look at this diagram, the net momentum of the system in vertical direction is becoming 0. Total momentum is becoming 0. No doubt, according to that law of conservation of momentum, immediately after explosion, that system should gather momentum only along the horizontal direction. So, no doubt, the third fragment should move in a horizontal direction. Mass of this third fragment also will be equal to m by 3. And with how much speed that third fragment is moving, we have to find out. Then by applying law of conservation of momentum here, before explosion, the net momentum of the bomb in the horizontal direction will be equal to m into 100, will be equal to momentum just after explosion will be equal to m by 3 into v. Therefore, v will be equal to 300 meter per second we are getting. This is the magnitude of velocity of the third fragment, and the third fragment is moving along positive x-axis. No doubt, the third fragment should move along positive x-axis only. Okay. Look at this example. A rocket set for vertical launching has a mass of 50 kg and containing 450 kg of fuel. It can have a maximum exhaust speed of 2 km per second. If g is equal to 10 meter per second square, what's the minimum rate of fuel consumption to give an initial acceleration of 20 meter per second square to the rocket? Okay. In case of rocket propulsion, majorly 2 forces are acting over the rockets. One force is nothing but the weight of the rocket, mg downwards. And the second force is the force exerted by those gases over the rocket. Total 2 forces are acting. The force exerted by gases over the rocket, we call it as upward thrust. This upward thrust will be given by relative velocity into dm by dt is the equation we are having. Velocity of the gases with respect to the rocket value into dm by dt. So if you look at this diagram, it is very clear. Unless until that thrust dominates than the weight of the rocket cannot accelerate in the upward direction. Therefore, the force equation for the rocket, instead of using that variable mass concept, in a simple way we can proceed here. In this case, simply we can write thrust minus mg will be equal to ma. In fact, by applying the idea of that variable mass system also, same equation we will get. You children, you can practice this equation in this way. Then this velocity of the gases with respect to the rocket into dm by dt is the thrust value. This is the formula of the thrust. That will be equal to, if you take this factor to other side, it will be m into g plus a. We are getting. In this particular question, our aim is calculation of dm by dt, the minimum rate of fuel consumption to give an initial acceleration of the rockets. In this diagram, actually, this A represents initial acceleration of the rocket at the time of firing. Okay, then from this equation we can write this velocity of the gases is given 2 kilometer per second they have given. So 2 into 10 raised to 3 meter per second into dm by dt. dm by dt we have to find out. And here m represents the total mass of the rocket including that fuel. Here mass of the rocket they have given 50 kg and contains 450 kilograms of fuel. Therefore, the total mass will be 500 into value of g they have given 10 plus initial acceleration of the rocket they have given 20 meter per second square. So this is 20. So this value will be equal to 500 into 30 we are getting. So 2 into 10 raised to 3 into dm by dt will be equal to this value. We cancel out this powers. Therefore, dm by dt from this equation will be coming out to be 15 by 2, nothing but 7.5 kilogram per second. 7.5 kilograms per second you will get. So it is one of an examples of variable mass system, rocket propulsion. This case is also very important for the competitive exams. Look at this part. A spring balance is attached to the ceiling of a lift. A man hangs his bag on the spring and the spring reads 49 newtons when the lift is stationary. If the lift moves downwards with an acceleration of 5 meter per second square, the reading of the spring balance will be. Okay. Already you have studied the apparent weight of a man in a moving lift. So whatever the equations you have practiced for the apparent weight of a man in a moving lift, analogously, same equations you will get in case of what we call a spring balance, which is suspended from the roof of a lift. When the lift is accelerating downwards, here initially when the lift is stationary, the reading of the spring balance is given 49 newtons they have given. When the lift is stationary, reading is equal to 49 newtons they have given. Nothing but when the lift is stationary, reading is nothing but mg only. Mg will be equal to 49 newtons. Now we have to find out the reading of the spring balance when the lift is accelerating downwards. When the lift is accelerating downwards, the reading of the spring balance will be given by mg minus ma. So this will be equals to mg. When the lift is accelerating upwards, reading will be mg plus ma. All these equations you have studied. So in this case, it will be mg minus ma when the lift is accelerating downwards. So this will be ma into g divided by g. Let us modify this equation. So this will be mg into 1 minus A by G we are getting. Mg value they have given it as 49 into 1 minus the acceleration of the lift in the downward direction they have given 5. To get the nearest answer, we can take acceleration due to gravity as what we call 10 we can take G. So this will be equal to 49 into 1 minus 1 by 2 we are getting. By solving this, we will get the answer to this particular question. This is an example of the apparent weight of a man in a moving lift. Okay, come to the next question. The coefficient of static friction between the two surfaces is 0.8. The tension in the string shown in the figure is. Okay. First of all, let us investigate the condition for the tension to be established in the string. Look at this diagram. Initially, let us assume there is no connection between the block and the string. Just imagine like this. Down the plane, the force which is acting over the block is nothing but mg sin theta. Up the plane, friction force will act. See, if mg sin theta dominates than maximum available friction, nothing but limiting friction, then only that block can slide down the plane. If mg sin theta is less than FL, then block does not have any tendency to slide down. Block will not slide down. If mg sin theta is less than FL, block will not slide down. For the block to slide down or accelerate downwards from rest, mg sin theta should dominate than FL. Under that condition, like when mg sin theta is greater than FL, under this condition, if string is connected to the block, then string will become tight. If string is absent, if mg sin theta is greater than FL, block will slide down. If string is present, string will become tight and tension will be established in the string. Then the resultant of that tension and friction will balance the downward force acting over the block, nothing but mg sin theta. Okay, in this particular example, now the condition for the tension to be established in the string is mg sin theta should be more than limiting friction. Okay, then mg sin theta is greater than FL, mu into normal force. Here, normal force will be balanced by mg cos theta. Over the inclined plane, n and mg cos theta will be balanced. So directly I will write FL. FL is nothing but mu into normal force. Normal force is nothing but mg cos theta. So from this we can write tan theta is greater than mu. So this is the main condition for the tension to be established in the string. So according to the data what they have given, whether tension is established in the string or not, let us see that part. In this example, mu value they have given as 0.8 they have given. And this angle of inclination they have given as 30 degrees they have given. Now let us calculate the value of tan theta, nothing but tan 30 degrees, 1 by root 3. So this value we can rearrange it as root 3 by 3, 1.732 by 3. So 0.57, something we are getting. So tan theta is coming out to be 0.57, or even if you take it as 0.6, here tan theta is having this value, and mu they have given as 0.8 they have given. For the tension to be established, tan theta value should be more than mu. But here tan theta is less than mu it is coming. Therefore, no tension will be established in the string in this particular example. While solving this type of questions, should be very, very careful. So answer to this question will be 0. Okay, come to the next example. A upper half of an inclined plane with inclination theta is perfectly smooth, while the lower half is rough. A body starting from rest at the top will again come to rest. Again will come to rest at the bottom if the coefficient of friction for the remaining half is given by. Okay. In this example, half of the inclined surface is smooth, they have given. Remaining half of the inclined plane is given rough. Here one block has started from rest and finally it is coming to rest at the bottom. We can solve the same question by different ways. One of the best methods of solving this type of questions is by applying work energy theorem. In this particular example, initial kinetic energy of the block is equal to 0 and final kinetic energy of the block also equals to 0. No change in kinetic energy. If you observe here, which forces are doing work? Down the plane, mg sin theta force is acting. Up the plane, kinetic friction is acting. While that block is sliding, this kinetic friction will act only in the second part of the inclined plane. This portion only friction is acting. Mg sin theta will act from very beginning until it reaches the bottom of the inclined plane. So from the diagram, we can tell very clearly that until that block reaches the bottom of the inclined plane, mg sin theta is doing positive work. That means until that block covers the entire length of the inclined plane, yes, that mg sin theta is doing positive work. Friction comes into play as soon as that block enters over that rough surface, remaining half, lower half of the inclined plane, and that friction is doing negative work. In this particular example, as there is no change in kinetic energy of the block, the amount of work done by that mg sin theta should be exactly equal to the amount of work done by that kinetic friction. Otherwise, directly if you apply work energy theorem equation, according to work energy theorem, we are having work done by all forces is equal to change in kinetic energy. Here only two forces are doing work. See, this is the situation we are visualizing after resolving mg into components. If you visualize other forces also which are acting over the block in this example, actually mg we resolved into two components in this example. One component perpendicular to the inclined plane, nothing but mg cos theta. Other component is parallel to the inclined plane, nothing but mg sin theta. That inclined plane will give normal force to the block. These are the various forces. Actually, total three forces are acting. One is mg, second one will be normal force, third one will be frictional force. We resolved mg into components, mg cos theta and mg sin theta. In this particular example of that block sliding down over the inclined plane, normal force and the component of mg cos theta, they are not doing work. Okay. And only mg sin theta and the friction they are doing work as far as that inclined plane is concerned. Okay. Here work done by mg sin theta plus work done by kinetic friction should be equal to 0 because there is no change in kinetic energy of the block. Work done by all forces is equal to change in kinetic energy. Final kinetic energy is 0. Initial kinetic energy is also equals to 0. So from this we can write mg sin theta is doing work from very beginning until it reaches bottom of the inclined plane. So work done by mg sin theta will be given by mg sin theta into s. And friction is doing work only when the block is moving over the lower part of that inclined plane. That means it's doing work only for the block moving s by 2 distance. So this will be negative. Work done by the kinetic friction will be negative. Minus Fk into s by 2 will be equal to 0. So from this equation we can write mg sin theta into s equals to Fk into s by 2. You can eliminate that s in the equation. From this part we can write mg sin theta equals to Fk can be written as mu k into normal force. Mu k into normal force. Mu k into normal force divided by 2. So one more equation we can write it as mg sin theta will be equal to mu k into normal force will be balanced by mg cos theta factor. Therefore we can write it as normal force as mg cos theta divided by 2. Then by solving this particular equation, that mu k, coefficient of kinetic friction between the block and that bottom, lower bottom inclined surface will come out to be 2 tan theta we are getting by solving this 2 tan theta. So this first option will be the answer to this particular question. Okay. The rear side of the truck is open and a box of mass 20 kg is placed on the truck 4 meters away from the open end. Mu k value they have given, g is equal to 10 meter per second square they have given. The truck starts from rest with an acceleration of 2 meter per second square on a straight path, straight road. The box will fall off the truck when it is at a distance from the starting point equal to. Okay. So it's an application example of what we call non-inertial frame. We can solve this question from non-inertial frame of reference. Means from that truck frame of reference we can solve it. Look at the scenario, what they have given in the question. Here a block of some mass small m, which is kept at a distance 4 meters from the open end of the truck. Here truck is accelerating along positive x-axis. Here truck comes under non-inertial frame of reference as it is accelerating. This value they have given as 2 meter per second square. When we look at this block from truck frame of reference, that block will be totally acted by different forces. One is mg, second one will be normal force, third force will be pseudo force, and the fourth force will be kinetic friction. These are the 4 forces which are acting over the block. And here block is accelerating along negative x-axis with respect to the truck. Okay, now let us write down the force equation for the block with respect to the truck. Here, when truck is accelerating along positive x-axis, it is given that box is falling down. The force equation for this block with respect to the truck will be ma minus fk is the net force. Ma minus fk is the net force that will produce acceleration in the block with respect to the truck, nothing but ma dash. Ma minus mu k into normal force will be equal to ma dash. Ma minus mu k, normal force is nothing but mg ma dash. You can eliminate this value of m. You can eliminate m from the equation. So a dash will be equal to a minus mu k into g. So a minus mu k into g. Mu k value they have given it as 0.15. Into g value also they have given as 10. A value of this truck they have given as 2. A value they have given as 2. So 2 minus 1.5, nothing but 0.5 meter per second square is the acceleration of the block with respect to the truck. Okay. With this acceleration, how much time that block will take to fall down from the truck, let us find out by using simple kinematic equation. With respect to the truck, that block has to travel only 4 meters distance to fall down from the truck. So for the block, if you apply the kinematic equation with respect to the truck, S is equal to block has started from rest. Block has started from rest and traveling 4 meters distance to fall down from the truck. So S is equal to half into A dash into T square. A dash is the acceleration of the block with respect to the truck. And how much distance that block has to move to fall down from the truck? 4 meters it has to move. 4 is equal to half into A dash, already we got 0.5, nothing but 1 by 2 into T square. T square will be equal to 4 into 4. Nothing but T is equal to 4 seconds. That block will take 4 seconds time to fall down from the truck. Within this time, 4 seconds, how much distance that the truck is traveling, they're asking us to find out. Now, we can take the kinematic equation to the truck. Truck is moving with an acceleration 2 meters per second square. So, S is equal to half AT square equation I will take for the truck. Don't get confused between these accelerations. Truck is moving with an acceleration 2 meters per second square. With respect to the truck, block is accelerating along negative x-axis with a value 0.5 meters per second square. So this is for the truck. I am writing equation half into acceleration of the truck will be equal to 2 into T square. T square is nothing but 16. So 16 meters is the total distance traveled by the truck before that block falls down from the truck. Look at this equation. In this particular equation, a force of 20 Newton is applied over the lower block of mass 4 kg. And they're asking us to find out the friction between these two blocks. Whenever, if you meet this type of questions, first of all, let us assume that the two blocks are moving together with common acceleration. If you take these two blocks together as the system, the total mass of the system is nothing but 6 kg. And the applied force is 24 newtons. Therefore, 24 newtons producing a amount of common acceleration in both the blocks, let us assume. So 24 net force is equal to MA, total mass of the system is 6 into A. So A will be equal to 4 meters per second square. Okay. Before we find out the frictional forces between these two blocks, first of all, let us find out the limiting friction that can exist between the two blocks. Limiting friction between the blocks will be given by mu into normal force. Here, relating to calculation of normal force also, several times I have seen students often they express one doubt. Between which surfaces you are calculating frictional force, between those surfaces only you should take normal force. It's a fundamental thing which must be remembered. Okay, in this case, mu value they have given it as 1 by 2 into normal force between the blocks, nothing but weight of the upper block, 2 into G. G value you can take it as 10. So 10 Newton is the limiting friction between these two blocks. Between these two blocks, limiting friction is 10 Newton, which means 10 Newton amount of maximum friction that can exist between the blocks. But how much amount of friction that will exist, that depends upon the applied force. Okay, here we assumed that the two blocks are moving with a common acceleration 4 meters per second square. To produce 4 meters per second square acceleration in the upper block, how much friction is required? Let us find out that. If you take upper block as the system, 2 kg, the friction exerted by the lower block over the upper block provides acceleration to the upper block. So for the upper block, force equation will be given by F is equal to MA. M is nothing but 2 into the acceleration is nothing but 4 meters per second square. So 8 Newton. So 8 Newton amount of frictional force is sufficient to produce 4 meters per second square acceleration in the block. Therefore, the frictional force between the blocks will become only 8 Newton, not the 10 Newton. 10 Newton amount of friction can exist. It depends upon the applied force. Still, if you increase this applied force, frictional force between the blocks also increases. Look at this example. The block of mass m given initial velocity 2v0 and a Planck 2m is given initial speed v0. Friction is present between the blocks only. Speed of the blocks when slipping stops is. It is one of the best examples of the frictional forces, kinetic friction. We know that kinetic friction always opposes the relative velocity between the blocks. If you look at the upper block is having velocity 2v0, and that what we call the lower block is having velocity v0. So velocity of the upper block with respect to the lower block will come out to be, so say for example, velocity of the upper block we name it as A, lower block as B. Say for example, velocity of the upper block with respect to the lower block will be equal to VA bar minus VB bar. Velocity of the upper block will be 2v0 I cap minus velocity of the lower block is nothing but v0 I cap. This is v0 I cap. The velocity of the upper block with respect to the lower block is along positive x-axis. Therefore, this upper block of mass m will experience kinetic friction along negative x-axis. Therefore, that lower block of mass 2m will experience kinetic friction Fk along positive x-axis. So, from the direction of these frictional forces, we can understand that the friction which is acting over the upper block will reduce the velocity of the upper block from 2v0 value. And the frictional force which is acting over the lower block will support the velocity of the lower block. Therefore, the velocity of the lower block will increase from the value v0. So, as the time advances, in this particular example, the velocity of the upper block is decreasing and the velocity of the lower block is increasing. At one particular instant, these velocities of the two blocks will become equal to each other. Okay, in this particular example, when we take upper block and lower block together as the system, these two blocks together if you take as the system, these frictional forces will become internal forces and they cancel with each other. Therefore, the total momentum of the system remains constant in this example, as the system is totally free from the external forces. That common velocity of these two blocks we can calculate by applying the conservation of momentum concept here. See, in the initial state, upper block is having speed 2v0 and the lower block is having speed v0 in the beginning. After some time, they attain the common velocity. Suppose this is v and the speed of the other block also v. By applying conservation of momentum to the initial state, to this initial state and the final state, in the initial state total momentum will be given by m into 2v0 plus 2m into v0 is the total momentum in the initial state. In the final state, total momentum is nothing but 3m into v. So 4m v0 will be equal to 3m into v. So common speed will be equal to 4v0 by 3. 4v0 by 3 will be the answer. So we can handle this type of numericals by applying the concept of conservation of momentum. Okay, look at this example. A conveyor belt is moving at a constant speed of 2 meters per second. A box is gently dropped on it. The coefficient of friction between them is 0.5. The distance that the box will move relative to the belt before coming to rest on it is. Here, one conveyor belt is moving with the speed 2 meters per second. A box gently dropped on it. Okay. And the coefficient of friction between them is 0.5. The distance that the box will move relative to the belt, they're asking us to find out before coming to rest on it. For the box to come to rest with respect to the belt, with how much velocity that the belt is moving, that the box also should get the same velocity. Then with respect to the belt, the velocity of the box will become 0. Okay, now let us look at the box from the belt. Belt is moving with constant velocity only. So as soon as that box is kept over the belt, with respect to the belt, that box will have velocity in opposite direction, 2 meters per second, 2 meters per second. And it will experience friction along positive x-axis, more specifically kinetic friction. So with respect to the belt, it will experience a friction along x-axis, or it will accelerate along x-axis. The body always accelerates along the direction of the external force or total force. The total force will be Fk. So block will accelerate along positive x-axis with respect to the belt, and moving along negative x-axis. So in this particular example, after some time, the velocity of the block with respect to the belt will become 0. First of all, let us find out this acceleration of the block with respect to the belt. Fk will be equal to mu k into normal force, nothing but mu k into mg. This is only the net force acting over the block, nothing but ma. So a will be equal to mu k into g. This is the acceleration acting over the block along positive x-axis. A is equal to mu k into g. Mu value they have given 0.5. G value you can take it as 10. So this will be 5 meters per second square. Okay, with respect to the belt, let us take the kinematic equation of that block. V square minus U square will be equal to 2as. So here, with respect to the belt, final velocity of the block will be equal to 0. It has come to rest with respect to the belt. And initial velocity will be 2 square, nothing but 4 is equal to 2. As it is accelerating opposite to the direction of motion, this acceleration will become minus 5 into s. So s will be equal to 0.4 meters. It is coming. So relative to the belt, after traveling through a distance of 0.4 meters, that block will come to rest. Next question. 3 identical cars A, B and C are moving at the same speed on 3 bridges. The car A goes on a plane bridge, B on a bridge convex upwards, and C goes on a bridge concave downwards. Let FA, FB and FC be the forces exerted by the cars on the bridges when they are at the middle of the bridges. They are asking us to compare these forces. It is also one of the very important examples for the calculation of the centripetal force. Look at this diagram. Initially, first car A is moving along a straight line, plane surface. Over this, 2 forces are acting. One is mg and other one will be normal force in vertical direction. This normal force is the force exerted by the car over the bridge or bridge over the car. Both are nothing but one and the same, action reaction forces. This force they named it as FA. This force we can name it as FA. Okay. In this case, that FA will be equal to mg. So very clearly you can understand this part from the diagram. This is the first case. Second case, that the car is moving over a convex bridge like this. All these, in all the cases that car is moving with the same speed only. Okay. 3 identical cars they have given, having same masses, and they are moving with the same speeds in all the cases. In this case also, in vertical direction, 2 forces are acting over the car. One is mg, second one will be normal force exerted by that bridge over the car. This normal force here we can name it as FB. For this car to come into the curved path, that car should be acted by some centripetal force towards the center of that circular path. That means unless until that mg dominates than what we call fb, that the car cannot be acted by the centripetal force and it cannot come into the circular path. So for that car to come into the circular path in this example, that car should be acted by net force towards the center. That net force will provide necessary centripetal force to the car to move along the circular path. So here it will be mg minus fb will provide centripetal force, nothing but mv square by r. mg minus fb will be equal to mv square by r. Therefore fb will be equal to the force exerted by bridge over the car in the second case will be equal to mg minus mv square by r. This is the second case. Come to the third case. In the third case, that car is moving over a concave bridge portion with the same speed v. So here also two forces are acting over the car. One is mg, second one will be the contact force or normal force exerted by the bridge over the car, that is fc you can name. For this car to come into the circular path in this track, net force should be acted towards the center, nothing but centripetal force. Centripetal force in this case will be given by fc minus mg, that is the resultant force which is acting towards center, will provide centripetal force, nothing but mv square by r. So fc will be equal to mg plus mv square by r. We are getting mg plus mv square by r. So if you compare these three cases, fc is maximum of the three forces. Okay, come to the next question. A right circular cone is fixed with its axis vertical and vertex down. A particle in contact with the smooth inside surface describes circular motion in a horizontal plane at a height of 20 centimeters above the vertex. Velocity of the particle in meter per second is. Here vertex is down like this. Here if you consider one small particle here, this particle will moving along a circular path like this. That particle will move along a circular path like this. Now let us identify which force is producing necessary centripetal force to that particle to move along the circular path. Here two forces are acting over the particle. One is mg and second one will be the normal force like this. This angle you can define as theta. This angle you can define as theta. This normal force you can resolve into two components, one vertical upwards, another in horizontal direction. Then with the construction, this angle also will become theta. I give the magnified view of the diagram. This is the inclined surface. This is the location of the block. You can think one force is mg, another one will be normal force like this. This normal force we are resolving into two components. This will become theta. This is n cos theta. This will be n sin theta. In this example, n sin theta and mg will balance with each other. So first equation. And the unbalanced force which is acting over the block in this case will be n cos theta. That will provide necessary centripetal force to that block to move along the circular path. So n cos theta will be equal to mv square by r. This is the second equation. Now let us solve these two equations. So tan theta will be equal to gr by v square we are getting. From the diagram we can make out that theta value, tan theta we can find out. This is given height h. This is theta. This is r. This will be the r, radius. This is the radius. Therefore, tan theta will be equal to r by h from the diagram equals to gr by v square. Then from this equation, it is very clear. R will be cancelled. So, v square will be equal to GH we are getting. So V is equal to root of GH. H value they have given, G we know. By substituting them, we will get the value of velocity of that particle which is moving along the circular path in this example. Come to the next example. A stone of mass 1 kg tied to a light inextensible string of length 10 by 3 meters is rotating in a circular path of radius L in a vertical plane. If the ratio of maximum to minimum tension in the string is 4 and G is equal to 10 meters per second square, the speed of the stone at the highest point of the circle is. So it's one of the examples of the vertical circular motion. In case of vertical circular motion, tension is not same. At different points, there will be different tensions. At the lowest point, let V1 be the speed of the particle. At the highest point, let V2 be the speed of the particle. At the lowest point, two forces are acting over the particle. One is mg and tension T1. So T1 minus mg will provide centripetal force to the particle. T1 minus mg will be equal to mv1 square by r. This is one equation. And the tension at the highest point will be given by, at highest point two forces are acting. One is mg and other one will be tension T2. mg and T2 both are acting towards center of the circular tract. Therefore, T2 plus mg will provide centripetal force at the highest point, mv2 square by r. The second equation. T2 minus T1, if you subtract m by r into v2 square minus v1 square we are getting. Okay. In case of a vertical circular path, the relationship between velocities v1 and v2 we can calculate as if like in case of a body projected vertically upwards. So we can take equation v2 square minus v1 square will be equal to minus 2gh. So this will be minus 2g into h is nothing but 2r. Means from the bottom, from this bottom, the total height will be equal to 2r. So this will be minus 4gr. This is v2 square minus v1 square equation. By substituting that, by substituting this value in the previous equation, we will get T2 minus T1 will come out to be, by solving, by substituting and solving, it will come out to be 6 mg. It is one of the very important equations which must be practiced. Okay. In this question they have given the ratio between the tensions they have given as 4 they have given. Maximum tension to minimum tension they have given 4. Nothing but tension in a string in a vertical circle is always maximum at the lowest point and it is always minimum at the highest point. So T1 by T2 ratio they have given as 4. So T1 will be equal to 4 T2. This relationship we can substitute in this equation what we got. Then it will become 4 T2 in case of what we call T1. We can substitute this part. Actually this is T1 minus T2. Sorry, this equation we can write. Tension at the lowest point is always maximum than at the highest point. So, sorry, here one mistake has done. So here actually T1 minus T2 after solving, after substituting these equations, we will get it as 6 mg. Here T1 is nothing but 4 T2. So from this equation we can write 4 T2 minus T2 will be equal to 6 mg we are getting. So 3 T2 will be equal to 6 mg. 3 T2 is equal to 6 mg. So T2 will be equal to 2 mg we are getting. T2 is equal to 2 mg. That is the tension in the string when the stone is at the highest points. For T2 already we are having one equation. T2 plus mg is equal to mv2 square by r is the equation we are having. In this case they are asking us to find out this v2 value. That means velocity of the particle at the highest point they are asking us to find out, V2. By substituting this value of T2, 2mg, in a second equation, it will become 3mg will be equal to m into V2 square by r. By solving this equation, we will get the value of V2, velocity of the particle at the highest point. Okay, the next question. A smooth track in the form of a quarter circle of radius 6 meters lies in the vertical plane. A particle moves from P1 to P2 under the action of three forces, always directed towards P2, and is all one force F1 is always directed towards P2 and is always 20 Newton in magnitude. Force F2 always acts horizontally and is 30 Newton in magnitude. Okay. Then wrong statement they are asking us to identify in this case. One point you just remember, if the force is constant, then the work done by that force is independent of the path followed by the particle. In this particular example, two forces are constant forces. One is F1 and other one is F2. F1 is always acting towards P2. It is constant. F2 is always acting horizontal. So the force, the work done by these forces independent of the path followed by the particle. It depends only over the initial and final positions. First of all, let us calculate the work done by that force F1. See, F1 is acting directly towards P2, always. Along that direction, we have to take the displacement. Therefore, the work done by that F1 will be given by force F1 into displacement along the direction of F1, which is nothing but 6 root 2, hypotenuse of that triangle. That value of F1, they have given 20. So 20 into 6 root 2, nothing but 120 root 2 joules. This is the work done by force F1. Come to the case of work done by the force F2. F2 is also constant force. It's acting in horizontal direction. That force F2 value they have given 30 Newton. 30 into displacement along the direction of that force. Along the direction of F2, displacement will be equal to 6. So this will be 180 joules. If you come to the case of F3, that F3 is always acting tangential to the circular path. Therefore, the work done by that force depends upon the path followed by the particle. So in this case, in a simpler way, we can write the work done by that force F3 will be equal to F3 into this total length of the path we have to add here. This total length of the path. So that total length of the path, it is 1/4 of the total circular path. 2 pi r by 4, nothing but pi r by 2. F3 value they have given as 15. 15 into pi into radius of the circular path is 6 divided by 4. So by solving this, it will come out to be 45 pi joules we are getting. If a force is constant with the time and with the position, that force is treated as a conservative force. If you look at the four options what they have given, first option is the wrong. Work done by F2 is 180 joules, work done by F3 is 45 pi joules, and F1 is conservative in nature. As it is moved slowly without any change in kinetic energy, work done by all forces is equal to 0. Work done by normal force plus work done by the external agency plus work done by mg will be equal to 0. Here, the work done by normal force is equal to 0 anyhow, that we know. It's very clear. Therefore, work done by this external agency F and work done by mg. Mg is also a constant force, we know. So in the case of constant forces, work done by the force is independent of the path. Therefore, mg is doing the work given by mgh minus mgh. mg is acting downwards, the displacement h is upwards. So mg is doing negative work here. Therefore, from this equation, work done by the external agency will become equal to mgh. Look at this question. A uniform chain of mass 300 grams and length 3 meters is held on a smooth table with 1/3 of its length hanging vertical. When released from the rest, it slides on the table and falls down. The kinetic energy of the chain at the time of leaving the table is. How do you handle this question? Let us see. Initially, 1/3 length of the chain is hanging from the edge of the table. Therefore, mass of this part will become m by 3. And for L by 3 length hanging from the edge of the table, the center of mass of that chain will be at a distance of L by 6 from the edge of the table. It is at the half distance. Total length is L by 3. So center of mass is at a distance L by 6 from the edge of the table. This is the first case. Now, from the table, now that the chain totally, it is coming down. Now total length of the chain is L, mass is M. Now center of mass of this part will be at a distance L by 2. If you look at these two diagrams, one point you can understand very clearly that the initial location of the center of mass is at a distance L by 6 from that what we call edge of the table. Now the center of mass will be at a distance L by 2 from the edge of the table. If you take edge of the table as the reference line where potential energy as 0, this you can take a reference line or 0 potential energy line. We are having freedom to construct reference lines anywhere, no problem, because the potential energy what we are calculating is the change in potential energy of the system. Okay, anyhow, this is the reference line. With respect to reference line, initially the center of mass of that chain will be at a distance L by 6. So initial potential energy will be equal to, as the center of mass is below the reference line, conventionally I will take it as a negative, minus m by 3. M by 3 is the mass of that hanging parts, into G into L by 6 is the distance of the center of mass. This is the potential energy of the hanging length from the edge of the table. If you come to the second part, it's a total length which is hanging. In this case, center of mass, potential energy of the chain, in this case will be given by minus mg into L by 2. So in this example, there is a loss in gravitational potential energy of the chain. That loss in gravitational potential of the chain will be converted into kinetic energy of the chain. So loss in gravitational potential energy will be equal to gain in kinetic energy. Loss is nothing but U1 minus U2. That will be equal to gain in kinetic energy. They are asking us to calculate the kinetic energy of the chain at the time of leaving. They are asking us to find out. By subtracting these two equations, you will get the result. See, as we people have come very close to the date of examination, finally, I would like to explain one important point. In this short span of time, you children, you just go through all the previous competitive examinations. Be confident, be cool, wish you all the best.